topics for this session are as follows. The important aspects of nonlinear behavior. I'll touch on strength-based versus deformation-based design, performance-based design, capacity design. Talk about modeling for practical nonlinear analysis, some limit states and demand capacity ratios, and then dynamic analysis versus static pushover analysis. And this is just the first session. The following sessions get into more detail. And the first session is an overview with not very many details. The scope, we're going to consider nonlinear analysis as being a design tool. The goal is to get useful information for design. The goal is not exact prediction of behavior. And I'll state many times during the seminar, exact prediction of behavior is impossible. Can't be done. Also, we're talking about assessing the performance of an existing design. So it's design analysis, not design synthesis. First topic is let's look at the important aspects of nonlinear behavior. There are two types of nonlinearity: material nonlinearity, which involves yielding, cracking, crushing, sliding, fracture, and a number of other things. And this is usually caused by inelastic behavior, but such things as gap opening and closing, which are not inelastic, are also regarded as material nonlinearity. Then there's geometric nonlinearity, which is caused by change in shape of the structure. And there are two forms of this. One is the P-delta theory, and the second is the true large displacements theory. And one of the things I'll emphasize is that for seismic analysis, P-delta theory is perfectly adequate. You almost never, and probably never, need to do large displacements analysis, and if you do, you're simply wasting computer time. The material nonlinearity is the more complicated of the two, and that's which I'll give most attention to in this session. So if you look at the main aspects of a force deformation relationship for a component or perhaps a structure, we have the initial stiffness. Somewhere in here, it may not be a well-defined point. There'll be first yield. There'll be then a region of strain hardening typically. You then reach some ultimate strength value. At a certain point, you'll use up the ductile capacity of the structure and reach some ductile limit. There'll be then strength loss. It may reach a residual strength value, which goes on for some considerable distance. And basically, those are the essential features if you were to apply monotonic loading. If you apply cyclic loading, you get a hysteresis loop. And one of the things you'll notice here is that the initial stiffness here is a lot larger than the unloading stiffness here. And that is stiffness degradation, which we'll talk about in a little more detail later. We have a structure and the structural components, and this little diagram indicates the two. For a structure, the force F is the load on the structure, whatever it might be, and D is some corresponding deflection. For the component, F depends on the component type, and we have many different component types. Here I'm just showing a simple bar where F is the axial force, and the corresponding deformation is D, the axial extension. If you have a plastic hinge, the F would be the bending moment at the hinge, and D would be the hinge rotation. And it can get more complicated than that. So if you're going to analyze a structure, you must know the component FD relationships. That's stuff you have to input to the computer program, and then the FD relationship for the structure will be calculated by the program using structural analysis. The types of structural components we might be talking about, a beam, a column, a beam-to-column connection, a viscous damper is a diagonal brace, a shear link and eccentrically based frame, a diagonal brace, a friction pendulum isolator, a rubber type isolator, maybe the foundation, components of many different types. If we look at a wall, we've got a pier, a beam. If we have a rather squat wall with odd-shaped openings, we run into issues, well, are there really components in here? What would the component be? But we sort of have to somehow come up with an answer to that question. Now, there's several complications in the FD relationship. And the first one is inevitably a lot of uncertainty. There can be substantial uncertainty in the strength and the stiffness and a number of other things. It's just inevitable. You don't know the strength of concrete. You probably don't even know the yield strength of the steel with any great accuracy. So there's going to be a fair amount of uncertainty in the strength magnitude and certain other things. Second complication is cyclic degradation. And what this illustrates is if you were to load the structure or component up and then cycle it once, you might get a nice fat hysteresis loop. If you cycle it several times to the same amplitude, you might find that the hysteresis loop will degrade. The stiffness can degrade, the strength can degrade, and as a consequence, the amount of energy which is dissipated also degrades. And that occurs under cyclic deformation. The converse of this is cyclic strength gain. Maybe when you cycle a component, it gets progressively stronger. For example, a buckling restrained brace typically exhibits this type of behavior. A reinforced concrete component typically exhibits the behavior on the preceding slide. A further complication is the effect of strength loss. If you do deform the structure or the component beyond the ductile limit, say out to this point, and then reverse it and pretend it through a hysteresis loop, maybe the strength in the opposite direction is not affected very much by the strength loss in this direction, and maybe it is. It depends on the component. So you may have to take this into account. It's just another complication. What happens after strength loss occurs? Further complication is the shape of the hysteresis loop. And I show here a non-degrading loop, the stiffness degrading loop I've already mentioned. Loops can also be pinched. And then if you have a buckling type behavior, you get a rather special loop, which is illustrated by the fourth of these diagrams. And these are not the only possibilities. There are several other possibilities also. But don't despair. The goal here is not to get an exact prediction of the behavior. That, as I've said, is literally impossible. The goal is to get useful information for design, and this is definitely possible. And what I'd point out is that when we use linear analysis to do design, it is far from accurate. If you run a linear analysis and you think you're getting accurate values of stresses and deflections, etc., think again, because you're not. It's by no means accurate, but it does give useful information for design. And we've used it for decades, if not centuries now. Linear analysis is not used because it's any exact or anything like that. It's used because it is useful. And what I would ask for nonlinear analysis is apply the same standard. Not is it exact, is it useful? And I would argue that nonlinear analysis, although it's more difficult, it's also more rational, and it can give much better information for design than linear analysis. So the second topic is, let's look briefly at strength-based versus deformation-based design. Strength-based design first. Again, this is the force-deformation relationship for a typical component. There's going to be some estimated force capacity, typically the nominal strength. You may apply a phi factor to get some usable force capacity for design. That's on the capacity side. On the demand side, you could calculate the force demand at working load somewhere here, apply a load factor to get the force demand at the factored load. And basically, you're going to check force demand versus force capacity at the component level. If the force demand at the factored load is smaller than the force capacity for all of the components of the structure, then your performance is satisfactory. What you do here is you can use linear analysis to calculate the demands, and this is usually okay because even up to the factored load, the behavior is pretty much linear. So if you're doing true strength-based design, you can use linear analysis. Now, earthquake forces are different. The conventional wisdom says it's not economical to design for earthquake, to design a structure to remain elastic during an earthquake. It will yield under a strong earthquake. So if you were to think of an elastic structure and you were to calculate the force demand on that elastic structure, that could substantially exceed the force capacity or the strength capacity of the structure or some or even possibly all of the components. However, the fact that the force demand on a linear structure exceeds the strength of the structure doesn't mean to say the structure is going to collapse. It would if the load were static, but it's not as dynamic, and so the structure does not necessarily collapse. And you will get some inelastic deformation well beyond yield, but this may not be excessive. If the structure has adequate ductility, the performance can still be satisfactory. So this gets us into deformation-based design, and the idea now is that you'll determine some deformation capacity, usually based on the amount of available ductility, and you'll calculate some deformation demand, and you check at the component or structure level whether the deformation demand is smaller than deformation capacity. If it is, the design is okay. And the key point here is that deformation demands must be calculated using nonlinear analysis because the structure yields and becomes nonlinear. Components with brittle behavior are different. Many components could have brittle behavior of the type illustrated here, and shear in reinforced concrete is a dominant example. There's little or no ductile capacity beyond yield, and components like this must usually be designed using the force or strength demand and capacity rather than deformation. So when you do deformation-based design, some components, the ductile ones, are going to be checked based on ductility, on deformation demand capacity ratio. Some other components, the brittle ones, are the ones that you decide will remain elastic even though they may not be brittle. Those would be checked based on strength or force, demand versus capacity. So summary, define deformation capacities for ductile components, define strength capacities for brittle components, and any other components you decide should remain elastic. Use nonlinear structural analysis to calculate the deformation and strength demands, and the performance is okay if all demand capacity ratios are smaller than 1. Simple in principle, not so simple in practice. Performance-based design. Conventional design codes do not explicitly establish a performance level. They imply that if your structure satisfies the code, then it won't collapse in a strong earthquake. But this is not explicitly stated. What performance-based design seeks to do is provide reasonable assurance, not a guarantee by any means. This is also probably impossible. Reasonable assurance that the design will satisfy a specific performance level. The most commonly used levels are immediate occupancy, which typically means little or no damage, life safety, which allows some damage but few or no injuries, and collapse prevention, which allows substantial damage but the structure should not collapse. And there are other levels which might be used. These are the 3 most common levels. The deformation capacities, these different levels are illustrated here. Immediate occupancy generally means little or no, little inelastic behavior. Life safety allows substantial inelastic behavior. Collapse prevention pushes the limits of the ductile capacity of the structure. Key steps: choose the performance level and the corresponding design loads. Define the demand capacity measures or the engineering performance measures. Engineering decision parameters, is another term which is used, EDPs. This could be drift, which is sort of a structure property. It could be plastic hinge rotation, which is getting down to the component level. It could be shear strength if you want the structure to remain, a particular beam, for example, to remain essentially elastic and shear. And there would be many other measures that you would use for doing demand capacity comparisons. You then get the deformation and strength capacities. Typically, strength is done calculating the design codes, ASC, ACI, etc. The formulas for strength capacity have been developed over decades. They've got hopelessly complicated, but they are well established. For deformation, we have much less to work with. The major source of information is ASCE 41, previously FEMA 356, and secondly would be experimental results. Having done that, You calculate the deformation and strength demands. This requires nonlinear structural analysis. And you calculate the demand-capacity ratios. If they're larger than 1, you either change the design, sharpen the pencil on the demand side to calculate the demands more precisely, or sharpen the pencil on the capacity side, and maybe your capacities were a little more conservative and you can stretch the limit a little. The available guidelines, the main guideline is ASC 41, there's FEMA 356. It strictly applies to performance-based design for seismic rehabilitation of existing buildings, but it can be applied to new construction. It provides some guidance on modeling for nonlinear analysis, not a lot, but some. And it provides deformation capacities for a wide range of structural components for the IO, LS, and CP levels. It's really pretty comprehensive from that point of view. However, this is sort of a first try at a code in this area. The modeling guidelines are rather simplistic, and it's argued that the deformation capacities may be too conservative. People indicate perhaps that they may tend to penalize reinforced concrete a little bit more than steel. This is not necessarily bad. I think it's probably a good idea to start off conservative, and maybe you can loosen up later on. It's a useful resource, but not yet a definitive set of rules. Let me skip that one. You can read that one if you want to in the notes. Let's look at capacity design. Let's go back and do this heck. This is sort of a philosophical point. It's rather obvious, but it is important. It's essential to establish formal demand capacity measures or engineering demand parameters, and to base a performance assessment on those measures. If you do a nonlinear analysis, you get lots and lots and lots of analysis results. And they're all important, and they certainly should be examined to make sure that your model and your analysis seem to be consistent. But for making a performance assessment, a judgment, the important results of the demand capacity ratios, really nothing else matters. Is demand greater than capacity or is it not? Now, there may be subjective judgments when you choose the demand capacity measures, when you establish the capacity values, and also when you calculate the demand values. There's subjective judgments, what should the capacity be for plastic end rotation? Is your analysis model okay or is it not? However, ultimately the overall process must be based on objective measures and demand capacity comparisons. It does not have to be perfect, and it never will be perfect. We have to learn to live with the uncertainty. Capacity design. The concept of capacity design, if you're not familiar with it, is that some components in the structure can safely be allowed to yield, and others should remain elastic. If we do not know which yield and which do not, we have to rely on the analysis to tell us. And this is really, when I say it can be dangerous, it probably is dangerous. You're not analyzing the actual structure, you're analyzing a model of the structure, and it's an imperfect model. So what you're getting, if you don't know where the structure is going to yield and where it's not, the analysis will tell you where the model yields and where the model doesn't yield. It doesn't necessarily tell you where the real structure yields and where the real structure doesn't yield. It's much better to decide in advance which components can yield and which must remain elastic. You do this as a design decision. You decide where yield is going to occur. What you can then do is design the yielding components to have sufficient ductility and the elastic components to have sufficient strength. Three major advantages. Firstly, if you do this, you can set up a more reliable nonlinear model. If you know where the yield is going to occur, you have a much better chance of setting up a good analysis model. Secondly, you can calculate more reliable demands and demand capacity ratios. And finally, and probably just as important, is the final design is likely to be a more forgiving design. That if the loading is a bit stronger than you expected, you're more likely to get proper behavior. And so it's a good, desirable design approach. It's not always possible, but it's a desirable goal. For a frame structure, typically what you would do would specify that the beams can be inelastic and bending, and maybe the columns can yield at the base because it's hard to stop them, and up the roof where you've got two beams in one column, maybe the column can yield there also. But in between, you'd want the strong column, weak beam behavior because this is basically desirable. And so you'd want the columns except the base and the roof to remain elastic. You might want the connections to remain elastic. You might want beams and columns to remain essentially elastic and shear. And you might want no damage in the foundations because that can be difficult to repair. If it's a shear wall, you might allow flexural hinging at the base of the wall, and you might allow inelastic behavior in the coupling beams. The remaining components probably should not yield. Bending in the wall everywhere except the base, shear in the wall everywhere, including in the hinge region, which can be particularly critical for shear, and again, the foundations. You can do capacity design without analysis. And this was, I think, probably Powell and Park in New Zealand sort of pushed this idea originally, and they didn't have nonlinear analysis much to work on. Nonlinear analysis is not essential for capacity design. What is essential is all the demand capacity ratios be less than 1. So if you say, well, I will allow these components to yield, for example, the shear wall example, you may allow a hinge to form at the base. Well, just design the hell out of the base and give it a whole lot of hinge rotation capacity. You might say that based on my judgment, this is sufficient even without analysis. Similarly, further up the structure, where you want to remain elastic in bending and elastic in shear, maybe you can make some pretty good estimates of what the capacities need to be without running a nonlinear analysis. Perhaps you could run some linear analysis or use some judgment. The advantage, though, of using nonlinear analysis is it can be more accurate. It can give you more accurate deformation and strength demands. Judgment or simple analysis can lead to over-design, and if the judgment is faulty, it could lead to under-design. And nonlinear behavior is pretty tricky. It requires, if you're not going to use analysis, it does require some pretty good judgment. Next topic, let's look at modeling for practical nonlinear analysis. We're getting now into the modeling phase. And please keep in mind the purpose of structural analysis. It's not an end in itself, it's a tool for use in design. The holy grail is accuracy, the exact prediction of behavior. And that holy grail does not exist. It'd be much better, I think, if the people on the structural analysis end in academia focused on usefulness rather than accuracy. The goal is not to get an exact simulation of behavior. You can't do this. The goal is to get demand capacity ratios that are accurate enough for decision making. Let's review the main aspects of nonlinear behavior. Initial stiffness, first yield, strain hardening, ultimate strength, a ductile limit, some strength loss, residual strength, and then a hysteresis loop. These are the types of things that we need to think about modeling for when you're doing nonlinear analysis. So we need a force deformation relationship for analysis, and this gets us into one of the first problems, is that if we were to load the structure monotonically, we might get the upper curve. If we were to cycle it a few times and get sort of an equivalent curve, this is going to be degradation of stiffness and strength, and it might correspond to something like this lower one. Now, current practice is to use a single curve, which uses it. It doesn't use this initial curve. It uses something which allows for a certain amount of degradation based on a reasonable amount of cycling. That's the present state of the art. So when you look at a force deformation relationship to use for analysis, it's not necessarily the monotonic loading one. It's somewhat degraded, allowing for a certain amount of cyclic behavior. In the future, I think what is going to happen is you might specify two curves, one which is monotonic and another one might be fully cycled, and you would specify both of them for analysis, and the computer program would transition from one to the other as it goes through the analysis based on the amount of cycling. But that's currently down the road a little bit. So talking about practical force deformation relationships, and one of the key things here, there are so many uncertainties that the best we can hope to do is to capture the main aspects of nonlinear behavior. You can't hope to capture all of the intricate details. If you can capture the main aspects, that's probably the best you can do. And there are two force deformation relationships shown here. The one on the left is from ASC 41. It's basically a bilinear relationship with some strength loss. The one on the right is the one which is used in Perform. It's a little more general. In fact, the ASC 41 FD relationship is a special case of the Perform one. And Perform has got these 5 points, YULRX. Y is an estimate of the initial yield. Then U is where you reach the ultimate strength. L is the ductile limit, and the strength lost down to R residual. And point X out here, typically you'll specify that to be some fairly large value, such that if you ever get out that far, you'll say, well, something has gone wrong or the structure isn't right. There really isn't any point in continuing beyond point X. So if this was, say, plastic hinge rotation and point X were 5% hinge rotation, if you've got that much hinge rotation, you may not, there's no point really in continuing the analysis, you may as well stop. And that is what Perform uses the X point form mainly, is to stop the analysis in case it goes, in case you get deformations which are unrealistically large. ASCE gives capacities, deformation capacities, for quite a wide range of components. Alternatively, it allows you to use experimental results. In fact, for dynamic analysis, it kind of really specifies you should use experimental results. And the I/O capacity is generally the onset of visible damage. At the other extreme, the collapse prevention capacity is usually at or close to the ductile limit. For some components, it allows you to come out to here, but these would be secondary components where the strength of the structure doesn't depend on the behavior of those components. Most primary components, it's either here or somewhat before you reach the ductile limit. And in ASC 41, a life safety capacity is typically about 75% of the CP capacity. And ASCE uses 41 uses the term acceptance criterion. In Perform, we use the term capacity. Perform can be used for ASCE 41, but it's not limited to ASCE 41. It's a good deal more general than that. And personally, I don't like the term acceptance criterion. It's what's wrong with capacity. One little detail about steel versus concrete in ASCE 41. The steel on the left, and typically this point here is the expected strength, and then you have some strain hardening possibly beyond that. In concrete, this point up here is usually the expected strength, and you come back to the Y point. You just have to be a little bit careful there. ASC 41 deals with steel and concrete rather differently in a number of respects, and this is one of them. If we look at an example here, this is a reinforced concrete beam. For a beam here, the performance assessment, you might say that bending behavior is ductile, so let's use the hinge rotation. Hinge rotation is a demand capacity measure and calculate the hinge rotation demand capacity ratio. The sort of model you might have is shown here in this diagram. There's a hinge forms here. A certain amount of the rotation is elastic, a certain amount of the rotation is plastic hinge rotation. And so you might get a moment rotation relationship for the end of the beam. This is the moment on the beam end, and this is rotation of the beam end. It looks something like this. This is a simple version. Elastic, perfectly plastic, and then possibly strength loss. ASC 41 says for I/O, the hinge rotation capacity from here to here. The plastic hinge rotation capacity is 1%, 0.01. Life safety, 2%, 0.02. Collapse prevention, 2.5%, 0.025. These are typical rotation capacities for a reinforced concrete beam. It's not quite that simple, but that's fairly typical. Now what I'm going to do here is to switch over to Perform and look at some aspects, and particularly I'm going to look at force deformation relationships. Don't worry about the details in this. This is the perform graphic interface. This is a simple 3-story steel frame structure. I'm just use this as an example. The interface is fairly sparse. On the right here is the graphics panel, and there's only one of them. And incidentally, if you use a higher resolution than I've got on the screen, the graphics panel is relatively larger, so this would be the minimum size for the graphics panel. Over here is where the data is input, and it gets kind of complicated. The reason being there's a lot of complicated input. So let's not worry too much about the details. Down here you can change the view direction, and if you want to do plans and elevations and things like that. There are 2 phases. The first phase is a modeling phase. I don't know if you can read that. I hope you can. The tooltip up the top says modeling phase. And the second one is the analysis phase. We're currently in the modeling phase, and there are a number of tools that you can use for doing the modeling. I'm not going to worry about the details. It is a node element model. You specify nodes, and you specify elements which connect the nodes. If you're a SAP user, SAP, you do objects, and then SAP will create the nodes and elements for you. We don't have that in Perform. Long-term, Perform will be incorporated into SAP, but right now it's a separate program. You can develop models within Perform quite quickly. You can generate nodes and move them around, all that kind of stuff. You can generate elements, move them around, all that kind of stuff. It doesn't usually take very long to build a model, even a fairly complicated model. Where you spend most of your time is in this task here, which is component properties, and another task over here, which is limit states. And I'm just going to look at component properties for now, and I just want to show the sort of things that you might have in the component properties. And you have quite a number of inelastic components available. Again, don't worry too much about the details, but if you're in a linear analysis, you don't usually need very many components. A frame element, a shell element, and a few other things. Nonlinear, though, you have lots of different types of nonlinear behavior, and you find you need a much wider choice of components. What I'm going to do is I'm going to go to materials here and just look at some possibilities. And this is an inelastic steel material without any buckling. And I've set up 2 of these things, and this is one of them. This is a very simple, elastic, perfectly plastic material. But this is as simple as you can get. And one of the things you can do in Perform is you can plot hysteresis loops here and have a look and see what they look like. 102. Okay. What I'm going to do here is show what the hysteresis loop would look like for this component. And I'm not doing any analysis here. I'm just in the task in Perform where you specify component properties. There are many different component properties you can specify. I'll look at that in a little more detail in a moment. But you may want to know what the hysteresis loop looks like for your component once you've specified the properties. I have specified the properties of this simple component. I just want to take a look at the hysteresis loop. And so I've said, let's go out to 0.02 rotation. 2% strain actually is 0.02% strain. This is an artificial material, don't worry. Then load it back to -2%, and up to +3%, then -0.3%. There's no degradation here. This is the simplest type of behavior with the simplest type of loop. This is the one option that you would have. Let's go to the second one here, which is a more complicated material. This now is trilinear when the strength is increasing, followed by strength loss. Let's go back and again plot the loops, and let's use the same ones as before. And that's the first one. Then back to minus 0.02 and then up to 0.03. Now, one thing you'll notice is that there's been some stiffness degradation. This stiffness here is smaller than the original one. Then we've got some strength loss, and after the strength loss, you start getting some more complicated stuff happening. And if we go to back up to 0.03 again, the last hysteresis loop is starting to get pretty complicated. And in fact, if we go to minus 0.03 and add this one, the last hysteresis loop has got very little energy degradation. Now, what is happening here is that for this particular component, I've used more of the capabilities of Perform to specify, firstly, a more complicated basic FD relationship, so-called backbone relationship, and then secondly, more complicated rules for the hysteresis loop, which involves some energy degradation. Now, I'm not going to go into the details. This is we don't have time to do it here. But the important point I want to make here is that you have a substantial amount of control over the hysteresis loop, and particularly in terms of this energy degradation. Here I've got a basic relationship. Then there's some additional strength loss information that you can specify, which is optional. There are incidentally some strain capacities. I've specified 3 of them. This is level 1, which would be immediate occupancy, level 2, which might be life safety, and level 3, which might be collapse prevention, which is right out at the ductile limit. These are some strain capacities that you might specify for this material. Then you can specify some cyclic degradation data. I'm not going to go into the details of this, but basically what this refers to the area of the hysteresis loop and the extent to which it degrades as the amount of deformation increases. And all of these properties except the basic ones are optional. You can use a very simple loop if you want. If you have a more complex loop, you just have to put in more information. And it can get quite complex. If we look at a material which buckles, and again I have one here, this buckles in compression and this seems to be elastic in tension. And if I plot the loop here, again, I've got to put this in again now, but that's the first leg, and it comes back and buckles. And then when it reloads after buckling, it's got some different behavior, and when it reverses after buckling, it's lost its buckling strength. It's a somewhat more complicated hysteresis loop, okay, without going into too many details. If we look now at a different type of force deformation relationship, I'm going to go to an inelastic, and I'm going to go to, actually what I'm going to do is go to a cross section to begin with here, and I'm going to come down to a column section. And this is a W14 by 193 cross section. The stuff in green here is obtained from some standard tables. It just you specify the cross section, and and these now are the section properties, but you can also assign a strength to these things. And what I've done here is assign some axial bending strength, and this means that there's a hysteresis loop. An interaction surface, not a hysteresis loop. So this now is a column with a PM interaction surface, and I've specified a cross section. The next thing I'm going to do is to go to an inelastic component. That's just a cross section as I've done now. And I'm going to pick a thing called a FEMA beam component. And the first thing this does, it uses that cross-section I've just defined, and the things in green are obtained from the cross-section properties. And then determines the elastic stiffness from the cross-section properties also. And some of the basic force deformation relation, it gets the strength of the component. But other stuff you have to specify yourself. And what I want to do here actually is get into a femur column, because I made a mistake there, and I want to do a femur column steel type. And this is the W14 by 193. It's got some elastic stiffness. It's got a basic force deformation relationship. Don't worry about the details. You have to specify both axial and bending properties. There's a yield surface, which has got some stuff here, and if I graph it, you can show what it's like. Those are the yield surfaces. I can show the basic FD relationship. There's also some deformation capacities. It's for level 1, which is IO, level 2, which is LS, level 3, which is CP. This now is just specifying component property. Now this is still a component. I defined a cross-section. Now I defined a thing called a femur component. And what I'm going to do next is to go into the next thing, which is a column. Let's do the next one. This is going to be a femur column, and it consists of four things. It's got an end zone. I hope you can see that in yellow. It's then got one of those things I just defined, and what is called a femur column component. And I was just looking at it a moment ago. That's for the first half, then for the second half, and then a rigid stiff end zone again. This is a column, so it is actually vertical. And so this has got is now a compound component, which is made up of 2 end zones and 2 of these femur column components. The femur column component dependent on a cross-section. It's starting to get a little bit complicated. The next step, which I won't show, I'll show that later on, is you would then assign this component to an element. So you'd go cross-section, the column component, the compound component consisting of several of these things, and I'll do more of these examples later, and then the element. Something else you can do here, and I'm going to go back to a previous example here. This is a beam now, and in the frame we're looking at, it has some bolted connections to the columns. It comes into the weak axis of the column, has a bolted connection. And this is what the component would look like for that beam. At the left end, it's got a moment release. That's the pin, the bolted connection. Then it's got some beams, and it's got a stiff end zone. And there's one additional thing here, which is a thing called a strength section. This is at the end here, a strength section. And the purpose here is to say, well, I've got a bolted connection. I'd like to make sure that the shear force on this bolted connection does not exceed the connection strength. And the way in which this is done is we have these basic components, which are the actual structural components, and then we have this particular strength section here, which enables us to check the shear strength at the bolts. And I can show the properties. And that particular strength section has got a strength of 100 kips. It's just a little arbitrary. So this is one way in a beam in which you can check the strength. The deformation would be checked using the other components. And if I come back in here and I look at this femur beam steel type, show the properties, I look at the deformation capacities. Those are now the deformation capacities. Okay. What I've done here is just going to go through and show a little bit about component properties and the hysteresis loops, and then how you can build up from a cross-section to a component such as the femur beam actually is kind of like a plastic hinge component. Then you can take a number of these and put them into a compound component, which you can use to model a complete beam or a complete column. And then what you also do is assign them to elements. Let me just illustrate that while I'm here. If you look at properties here, if I look at this particular beam, it's been assigned a frame member compound component, and the name of it is perimeter girder with no releases. If I show the properties, this is stuff we were looking at before. It's got an end zone, it's got a couple of basic plastic hinge components and another end zone. And if you want to, you can drill further down. We've already seen this, show the properties of this one, and this is stuff that we looked at before. It's just in a review mode. So that then is assigning the component to an element. I'm going to go back now to the PowerPoint. So we just did that, and we used Perform 3D to show deformation capacities, FD relationship from structural components. When you're building a model, most of your time actually is going to be spent in that component properties portion of the input. Defining the geometry is relatively simple. Defining the nonlinear component properties is far from simple. In a linear analysis, it's a simple process. You just give material properties, you're done. Elastic modulus, maybe a Poisson's ratio, that's it, you're done. Nonlinear, no way, you've just begun. That's the beginning. You have to know a lot more about your components. You have to be a much better engineer, basically. You have to have some understanding of nonlinear behavior. And there's no way in which the computer program can know this stuff. You have to know it, and you have to provide it to the computer program. And that is where you'll spend probably most of your time. The other one is in limit states, which I'll come back and look at later. Perform 3D does not have many built-in properties. When you look at computer programs for linear analysis, they've usually got the code equations built into them. The early computer programs didn't, but the new ones obviously do, and they're not much use if they don't have code equations built into them. It's not yet time, I think, for computer programmers to be making engineering decisions by building these types of things into a nonlinear analysis program, and in Perform 3D we haven't. In the future you can expect more built-in properties and procedures, but that's down the line a little bit. Next topic, let's look now at limit states and demand capacity ratios. Perform has a specific meaning for limit states, and the reasoning is shown on this slide. For a large structure, you can have a huge number of components, thousands of plastic hinges and things like that. Let's look at plastic hinges as a particular example. A large frame could have hundreds or thousands of plastic hinges. And for each of those plastic hinges, there's a demand capacity ratio. And if you had to examine each of those individually, it's impractical. It can't be done. So what Perform does is it uses limit states, quote unquote, to organize the demand capacity ratios into sets. And the sets are organized by the element or member type, by the component type or mode of action, and by the performance level. For example, a single limit state might cover the following. All of the girders in the perimeter frames of a structure. Maybe. You have a choice over this. Let's say all of the girders and all the perimeter frames, all of the plastic hinge components in those girders, and the rotations of those hinges, and hence the rotation demand capacity ratios, and demand capacity ratios based on the life safety level. That would be like possibly one limit state. And then, and you might have still 100 limit states for a complicated structure, maybe 200 limit states. It starts to get fairly complicated. Later on, we'll talk about if you have 100 limit states, you also may want to group them into related groups, and you can also do that. So a limit state takes demand capacity ratios and groups them into related groups. Later on, we can talk about it. You can then take groups of limit states, and you can arrange those in groups also. So a limit state in Perform has a usage ratio, and it's based on the demand capacity ratios that are included in that limit state. And in our example, 1,000 plastic hinges, and there's 1,000 demand capacity ratios, and the usage ratio is based on those 1,000 demand capacity ratios. How is that done? Well, a simple way, and the most conservative one, is out of all of those 1,000 demand capacity ratios, just take the biggest and say that is your limit state usage ratio. And that number should be less than 1 for the performance for it to be okay. So you're looking at the worst hinge in that particular case. That would be the simplest choice. But there are other ways, and here's an example. And this now gets us into earthquakes. is suppose you run analyses for n earthquakes, and n might be 3, might be 7. Actually, people have been running 28. 7 earthquakes, 2 directions, and plus and minus. There's a whole bunch of combinations. Let's say n is equal to 7 for the time being. You would consider each component in turn, basically each hinge in turn. And for that hinge, you've got 7 demand capacity ratios, 1 for each earthquake. Take the average value, the mean value of those for that component, and then the usage ratio for the limit state is the maximum of those mean values. So each hinge, you've got 7 values, take the mean, you've got 1,000 mean values, take the largest of those, that's the usage ratios for the limit state. Now the demand capacity ratios for some hinges, for some earthquakes may be larger than 1, possibly substantially larger than 1. But the biggest of the mean values would need to be less than 1. ASC 41 allows this method, and it is included as an option in Perform 3D. I'll demonstrate this later on when we show some limit states. So this is the way Perform basically takes an awful lot of stuff and distills it down to a few simple values for decision making. The limit state usage ratios distill the results of complex computations as simple values. And to say this, we've just said before, and I'm going to show some examples in a moment. Next topic, let's look at dynamic analysis versus static pushover, briefly. Dynamic analysis first, the steps are as follows. Apply the gravity load first. Usually the analysis can be linear. Not always, but usually. The earthquake load is defined by ground motion, seismograms or accelerograms. Typically you'll have both horizontal and vertical seismograms. Usually you'll only consider the horizontal motions. You can consider vertical motions and Perform 3D if you like, but it opens up all sorts of cans of worms, and usually we don't. So you run a nonlinear step-by-step analysis, step-by-step through time. It's a brute force approach. A typical time step might be 0.01 of a second or maybe 0.2 seconds. If you have a 20-second earthquake, it might be 2,000 or 1,000 steps. That means it's going to take roughly 1,000 times longer than a linear analysis because you're just repeating the analysis basically many times. At each step, and Perform does this calculation for you, it calculates the demands for every component. If it's 1,000 hinges, it calculates the rotation demand for every one of those 1,000 hinges. In some cases, incidentally, the capacity may also have to be calculated at each of these time steps, because sometimes for example, a hinge rotation capacity can depend on the shear force of the hinge. The larger the shear force, the smaller the ductility, the smaller the rotation capacity. And since the shear force varies during analysis, then you have to recalculate the capacity at every time step also. And Perform can do this. And then it calculates the component demand capacity ratios and the limit state usage ratios. At the very end of the process, if all the usage ratios are less than 1, you're okay. Otherwise, you've got to redesign or sharpen some pencils. That's dynamic analysis. It's a straightforward process, but it does require that you use ground motions and rather complicated and possibly time-consuming analysis. Static pushover analysis has been around as a way to reduce the amount of computation, basically. And this slide indicates the steps in pushover analysis. And firstly, you choose the load, you specify the gravity load vertically, and some horizontal load pattern. In this case, this is kind of looks like almost a uniform load pattern. You might be linear, or you might base the load pattern on the mode shape, or you typically would have several load patterns and run a number of different pushover analyses, one for each load pattern. But you don't worry about the magnitude of this at this stage, just the distribution. Then you do a static pushover analysis, which will give a nonlinear relationship between a horizontal load and horizontal displacement. The gravity load is held constant, and you apply the horizontal load. Then using a response spectrum, you'll estimate this point here, which is sometimes called the performance point, sometimes called the target displacement. This is your best estimate of whereabouts along this curve, where the deformations that would correspond to an actual earthquake. The way you get this is using a response spectrum. This is the representation of the earthquake. You then, at this point, you calculate the limit state usage ratios, and you check and see if they're less than 1. So two main steps: calculate the pushover curve and calculate the target displacement. Advantage and disadvantages of pushover: use a response spectrum rather than ground motions. Static analysis model is a little simpler than dynamic, not a lot, but somewhat simpler. And the analysis takes less computer time. But however, there are major caveats. Firstly, it is approximate, and the reason is it uses static analysis to represent dynamic loads and cyclic deformations. There's no cyclic deformation in a pushover analysis. And it does not work well for tall structures, and it doesn't work well for complex structures. So I'm going to go back here now to Perform 3D and look at limit states and a few analysis results. And this is now getting into the analysis phase, and there are a number of things here. I can specify load cases, and I'm not going to get any details here, but for example, here's one of the earthquake cases. And if you like, I can come in here and review the earthquake and a bunch of stuff like this. If you've ever done any computer programming, the graphic interface is the most important part for a program such as Perform. If any changes are made to the program, 90% of the programming effort goes in the graphic interface, only 10% probably goes into the number crunching. You can then specify what is called an analysis series. And let me spend a little while on here. You're going to run some analyses, but what Perform allows you to do is to make some variations in your analysis model at the time that you do the analysis. For example, here we're specifying some masses. What you could, and this is a particular analysis series called Series 1. What you could do is you could specify a number of different mass patterns, and when you come to run your analyses, you say, okay, I'll use one particular set of masses for Series 1, and I'll run a number of analyses with those masses. Then I'll create Series 2, and I'll use some different masses and run some different analyses with those masses. I don't have to create a new structure, I just have to create a new analysis series. The other thing I can do is choose whether or not to use p-delta effects. So you might run one analysis series ignoring p-delta effects, another one including them. And then you can also vary the damping. Later on today, I'll talk about damping. You can have modal damping or Rayleigh damping. And there's a bunch of other things you can do. You can actually even vary the strength of the components using upper and lower bounds if you wish. So you could actually analyze one structure which is rather weaker and another structure which is rather stronger without creating a complete new analysis model. I've done just one analysis series here. It uses some basic mass. It includes p-delta, and it's got 3% modal damping. And I've already run a number of analyses. And I'm going to come back in a moment and look at these. But first of all, let's just continue on with these analysis phase operations. This next one here is the mode shapes. You can plot and animate the mode shapes if you want it. It's fairly routine. Energy balance, we'll talk about this later on, but it gives you an energy balance. I'll come back to that a little later. I mentioned before that you can organize limit states into groups. If you have a couple of hundred limit states, you might want to organize them into related groups. You can do that. Then you can look at deflected shapes. And at the time that you do that, you can also do some other stuff. I'm going to plot the deflected shape. It's actually doing quite a lot of computation here. This takes a moment. And we'll start here. And notice that some of the elements have changed color. This is because the colors of these elements are based on the demand capacity ratios for certain things within those elements. And the coloring scheme is if it's blue means it's between 0.4 and 0.6 usage demand capacity ratio. Green means between 0.6 and 0.8, and yellow means between 0.8 and 0.1. And this is all immediate occupancy, but that's really, let's just choose all life safety states instead. And now you notice all the color disappeared because we haven't yet exceeded 0.4 on any of the limit states. And then we can plot this thing. See, actually the colors, there's actually still a few colors in there, but and then we can, if you like, animate this thing. And as it goes, you'll see that the colors will change as it gets along. You know, it's kind of cute to be able to do this. You can see how the usage ratios on these components change, and you can see where the hotspots are in the structure. That can be quite useful. We haven't yet got into true demand capacity checking. You can do plot time histories for a whole bunch of things. For example, I haven't really talked about this much, but these are connection panel zones. They're actual elements. And if I plot the moment which is being transferred there through this, you can do a bunch of things. I can also, for the same thing, I could plot a hysteresis loop. That's a hysteresis loop for that particular panel zone. You can see it's yielded. There's no worry too much about that. This is another one where what I can do is, for example, plot a moment diagram for, for a line of elements. That's the moment and shear diagrams for the gravity load case. There's some gravity loads on these things. And we're getting it here into the sort of thing that happens as the earthquake goes through. It's just showing the bending moment diagram. This can be useful for assessing whether the model is okay or not. Let's not worry too much about the details. Now we get into, I'm going to go back here and look at limit states, because this is what we're really talking about here. Limit states can be of deformation, strength, drift, deflection, or structure section type. I'll talk about structure section type later. Let me just do deformation and strength right now. And deformation, there are 9 deformation limit states for this simple example. That's not very many. First one is perimeter column rotation for immediate occupancy. Second, perimeter column rotation life safety. Same thing, collapse prevention. Then the perimeter girder hinge rotation, IO, LS, and CP. And panel zone shear deformation. The panel zones yield. Incidentally, in a linear analysis, you often don't need an actual panel zone element. You can estimate the loads on the panel zone from the forces and the beams and the columns. That's okay, but in a nonlinear analysis, the panel zone could be the weak link, and it could yield. In this case, it does. And if the panel zone yields, then you have to have a specific element that will yield. And in Perform, you have specific panel zone elements. They're single node elements, and they're very easy to specify. This is a limit state. It's not a very complicated one. A limit state consists of a number of conditions, and all I've got here is one condition. This is the panel zone shear deformation for collapse prevention. The element group is all the connection panel zones, so it just as all the connection panel zones. The element type is panel zone, and the component type is panel zone. And then the deformation type is going to be the shear strain in the panel zone. It can be either positive or negative. There, you could have separate positive and negative if you wanted. And it uses level 3, which is the collapse prevention capacities. And don't worry about this last DC limit. This enables you to adjust things up and down a little bit if you want to without going back and re-specifying the properties. And so there are, in this case, only 9 of these things, 3 for the columns, 3 for the beams, 3 for the panel zones. In a more complicated structure, there could be many more. There's also strength limit states, and here there are 2 of them. One, we have some gravity beams, and just to make sure the gravity beams are not overloaded, there's a bending moment strength section put at the middle of the gravity beams, and it calculates the strength demand capacity ratio at midspan on the gravity beams. That's pretty straightforward, and it's just to make sure that you haven't specified the gravity beams incorrectly. The second one is the perimeter girder connection strength, and I mentioned this one once before, that you have a bolted connection where the perimeter girders bolt into the weak axis of the column, and you just like to make sure that the shear strength in those connections is not exceeded. So you specify a shear strength, and then you specify a strength section. If you recall, we talked about that before. Position it at the end of the beam, and what this limit state does is to calculate the strength demand capacity ratio on that section. So it just checks to make sure your bolted connections are okay. So now we can go back to the key thing here. This is now looking at demand capacity ratio, usage ratios actually. Demand capacity balance is what the little icon means. And I'm going to go to the all life safety group, and this is an earthquake. I'll plot it. And what this is showing is how the usage ratio for the limit states varies during the earthquake, and this is out to 15 seconds of earthquake. And at the end, the worst one here is the perimeter girder connection strength, and it has a usage ratio of around about 0.88. The next one is the perimeter girder rotation for the life safety level, and it reaches only a usage ratio of 1. Next one down, the perimeter column rotation. Next one down, the panel zone shear deformation. And the last one, which is constant, which is the bending moment at the middle of the gravity beams. That doesn't change during the earthquake. Now that is, shows what for a single earthquake. And basically here's level, the 1.0 level. If everything is below 1.0, you've satisfied all the performance requirements. If any of these limit states is above 1.0, you have to do something, maybe revise the design. Now, that would be what you would do for the case where I said that you use the maximum, the worst hinge. Let's look next at the one where you do this averaging process, which is permitted by ASC 41. And this is a combination and envelopes option. I'm not going to go into any details on this, but basically I've defined here a combination which has got 4 earthquakes. Normally you would use 7, but I've just happened to use 4 as an example. And I'm going to choose the max, and this is just going to use the worst thing. And let's just plot it. And actually I want to do a oh, here we go. I want to do a limit state group and just all life safe. What I just did was all of the limit states. There's way too many of them. So I'm just going to limit them down to the life safety limit states. And if I click on this, this is the perimeter girder connection strength, and it reaches a maximum value. All the earthquakes give the same result for this. Look at the next one down, which is the perimeter girder rotation. The first earthquake gives this value for the maximum rotation of any hinge in a perimeter girder. Second earthquake, third earthquake, fourth earthquake. I'm using the max of max, so the usage ratio for this would be this value here, 0.81. But there's another option here, which is the max mean, and that's the one I talked about, where you take the mean at the component level and then take the maximum of those means. When I plot this, and I look at this one again, okay, here are the 4 earthquakes, but this is the value which is based on the mean value. A good deal smaller than that. Some people say, gee, this really may not be such a great idea. Maybe not so much for deformations, but if you're designing something for strength, maybe using the mean value for the strength demand capacity ratio isn't really such a great idea. Maybe you should use mean plus 1 standard deviation. And if you think about it, it actually is maybe not a bad idea. And you can also do that. There's an option here for mean plus n sigma, and n is here 1. If we plot this, and we do the same thing here, it's now rather more conservative because it's using the mean plus 1 sigma. Now, I'm not going to spend any more time on this. Let's make sure, because I want to do pushover analysis. The important thing about these last 2 things I've done is that this is really the bottom line when it comes to making decisions about whether the design is satisfactory or not, is looking at demand capacity ratios. And Performer's got these two tools here. The one we looked at where you can do a single earthquake or a single pushover, actually, if you wish, and the one where you can do a combination. And I did one particular example. You can also combine pushover analyses if you wish. Now let me do also a pushover analysis. That was earthquakes. And this is now, it's going to be horizontal, the push in the horizontal one direction, and it's a uniform pushover, and there are 4 different pushover analyses here. I'll just look at one of them. And I'm going to, first of all, plot the pushover curve. And this is what it looks like. And there's some p-delta effect, so there's some loss, strength loss as it gets into the buckling range. There's a couple of limit points here. And this one is the perimeter girder rotation for the life safety state. This is where the usage ratio for that limit state reaches 1.0. Later on, the second one, which is the perimeter column rotation, this is where that reaches 1.0. Now I'm going to estimate a performance point or a target displacement based on this. And basically, if I get a performance point or target displacement which is before this occurs, then at the target displacement, my usage ratios are all less than 1, the performance is okay. If the target displacement is out here, then the usage ratio for this limit state would be larger than 1, the performance is not okay. I have to define a spectrum, and I'm not going to go into any details here. This is the theory of this is a little complicated. It's explained in the user guide and some other stuff. But there's a family of spectra that you use, and these are for different amounts of damping, 2%, 5%, 10%, 20, 30, 40, and 50% amount damping. I don't want to go into the details. The way in which perform works is this, I have to come up with a bilinear approximation of this curve. And I don't know if you can see it, there's a little circle there which has to lie on the curve, and AB over AC has got to be 1.0. And I got 1.05, and yeah, that's not bad. That was a bit of a nuisance, wasn't it? I had to do it. The other thing I can do is I'm just going to do a left click, and it'll generate it for me. And it doesn't always work, but that's a lot faster than the first thing I did. And what I've done is generate here 3 trial points. And I'm going to find out that this is along the capacity curve, which is the pushover curve. I'm also going to plot a demand curve. And let me do that next. There are a number of different pushover methods. I can't go into the differences here. It's too complicated. But there's the coefficient or displacement modification method. There's a new method of FEMA 440 linearization. There's a much older capacity spectrum method. I'm going to use the FEMA 440 method. And without going into too much detail, I'm going to plot a demand curve. And basically, where this demand curve plot crosses the capacity curve, this is the target displacement. So I made a reasonable estimate, but let's go in here and make a better estimate. It looks like it's about 0.032. Let's clear these. And that's still not great, but that's better. And here it is. It's 0.0327 is what it says is the drift ratio, 3.2%, and it's okay. Now this demand curve actually, which is this curve, has some value. Without going into too much detail, it tells you sensitivity information. What this says is that if you were to increase the stiffness and strength of this curve so as it came up here and passed through this point, so the same curve but with an increase in stiffness and strength in the same proportions, then this would be your target displacement. Correspondingly, if you were to reduce the stiffness and strength so as it passed through here, this would be your target displacement. It gives you some idea of what would happen, at least according to the pushover theory, if you were to vary the design. And that's, notice here it says vertical. If I make this one radial, this is a little bit different. What this says is that let's keep the stiffness constant, but just increase the strength. So you would expand this curve out radially rather than vertically. And what this says, if you just increase the strength without changing the stiffness, it's not going to make too much difference in the target displacement. However, the curve will be rather different, so it'll be further back on the curve. Without going into details, this gives you some sensitivity information. One of the problems with dynamic analysis is you don't get any sensitivity information. So it's kind of difficult to figure out how maybe you should change your design. Pushover analysis has this little bit of an advantage. Now, we've got here 0.032. Let's just come back over here to the demand capacity. Let's use the same load case, and I want the same life safety limit states, and I'm going to put in here a 0.032 drift, and then plot. And this now shows, during the pushover, how the usage ratios vary. This is for the perimeter girder rotations. This is for the perimeter girder connection strength. This, I think, is for the column rotations. This is for the panel zone rotations, and this is for the girder bending strength. One of the things you may notice is, if the dynamic analysis, these top two were reversed, but this is not necessarily a response spectrum that corresponds to those dynamic analyses. So this is what you would do if you were using pushover, and you can also combine pushover here if you want to as well. I'm not going to go into the details on that. Okay, having done that, conclusion. What I just talked about and demonstrated from performance, I'll go into much more detail in the following sessions, is the current state of the art. Future methods are likely to be based on probability. There's a lot of work being done this in the academic world, is rather than this deterministic method, probabilistically. What is the probability that something is going to happen? A simple example might be that, suppose you said it's okay for the limit state usage ratio to be maybe larger than 1. What is the probability that the usage ratio limit state will be larger than 1? It might be kind of nice to know that. This is the kind of sort of thing that people are working towards. I should warn you that it requires huge amounts of computation. We're talking here about doing 7 earthquakes. We'll think maybe 70. It's going to require huge amounts of computation power in order to use these methods. So they're down the road quite some distance, I think. However, future methods may do this, and may also use performance measures which are rather different from deformation like hinge rotations. The cost of repair, this is a dollars downtime and deaths type thing. Could you make an estimate of what the repair cost will be? And then if you're using demand capacity, well, the capacity is how much can you afford, and the demand is how much will it cost. If you want to look at downtime, the capacity is how long can you afford to have your facility out of operation, and the demand is, well, how long will it be out of operation, at least according to these analyses. And if you want to get into deaths, how many deaths are you prepared to accept compared with how many it's estimated will occur. This is what's down the line a bit, but for the present, the sort of deterministic methods I've talked about in this session are enough of a challenge. So conclusion, this session is an overview. The later sessions consider narrower topics. The next 2 sessions consider modeling and performance assessment for frames and shear walls respectively. And then the last one is more detail on nonlinear analysis methods. You're going to be pretty tired by then. That's kind of the young people who want to know how things work a little bit more. And we have a few minutes. Any questions?
What's the memory limit for the structure analysis for the performance 3D? How many memory size? What's the number of members or what number of hinge limits?
Very large, larger than you'd want to do, I think. 50-story buildings, yes, no real problem. 10-story building is a small structure. Perform has been used for I think even a 100-story building, shear wall building has been used. And that's with the current Windows operating system. When you go to Windows Vista, which has got 64-bit, it's going to be huge. The limitation isn't so much the size of the structure, it's the speed of the computer, because as the structure gets larger, the analysis time gets larger also, and it can, for very, very large structures, it can be a matter of days, unfortunately, for a nonlinear dynamic analysis. But there's really no limit on the size.
The earthquake records, is it built in, the number of them, or do you have to get them from some source? Where do you get them from?
About the earthquake records, you have to input them into Perform. It's typically you'll have the earthquake record available as a text file, and then you import it, and you have to import each one. But you can set up a library of earthquake records, and you can use them across different structures. It is also possible to process them outside Perform and then just bring the processed files in. It's not a major issue unless you've got hundreds of earthquakes. Oh, anywhere. You can go online and get... choosing the records is a bit of a black art. This is a matter of debate. If you have these 7 records, there are certain rules that ASC 41 and other documents establish that you should follow. But it is admittedly possible to kind of cherry pick your earthquakes a little bit. This is a matter of intense debate in the academic community about exactly how do you pick the earthquakes, and this is something of an unresolved issue. Computer program like Perform 3D is just an analysis tool. It assumes that you have created your design and you want to assess the performance of that design. If your design is not okay, if it's either unconservative or maybe too conservative, it doesn't really give you any guidance on how you should change it. That's up to you as the engineer. And I would come back and I gave some reasons why capacity design is a good idea. That's a 4th reason why capacity design is a good idea, is if you're using capacity design principles and you run into this issue that perhaps the shear demand at the hinge level of a shear wall building is too large, well then you have to increase the shear reinforcement at that location. It's a fairly simple decision. But it could be much more complex than that, and all I can say is it's an analysis tool, it's not a design tool. If your coupling beam is governed by bending, in the unlikely event that your coupling beam is governed by bending, then you put in bending hinges and use, for example, a femur beam component. And you use hinge rotation as your demand capacity measure. If, as is more likely, I think, the coupling beam is governed by shear, then you put in a shear hinge and you use shear deformation as your demand capacity measure. It's a no-brainer, actually. You have to know whether it's governed by shear or by bending. If you don't know, you should know. I will talk about that specific issue in the 3rd session.
One more question is, have you ever run into any instability problem? In other words, just program just go crazy and die in the computation?
Yes, and not often. I don't want to brag too much, but I think Perform 3D is remarkably stable. Now, if you do some crazy things and specify some stupid properties, yeah, it can give trouble. But on the whole, I think it's proven to be rather good. And I'll talk about that in session 4 also.